Okay, in order to understand the structure of the cluster compounds, two things we have to understand, like why the metal-metal bond is formed, what is the reason behind it, uh, what is the best way to understand this metal-metal bond formation. Simply, we say that uh, uh, we just count the number of electrons for the overall molecule, and how many numbers is less. So depending upon that less number of electron, we make count electron pairs, and that many number of bonds are there, metal-metal bonds are there. With that, we make a mathematical calculation, right? However, it is necessary for us to understand uh, how this metal-metal bond is formed. Okay, it is best to know about the isolable strategy or analogy. Then if you apply it to any cluster, then it is easy for you to have perfect understanding of it. This is a page from the Nobel Prize, and the Nobel Prize in Chemistry for the year 1981 was awarded to these two gentlemen, Professor Kenichi Fukui of Japan and Roald Hoffman of USA. Okay, both of them were awarded for their theories, which are developed independently. They worked in two different organizations, I mean, two different countries and different labs, and they developed theories almost the same concerning the cores of chemical reactions, understanding chemical reactions. Right? We all know that chemical reactions are all nothing but just bond breaking and bond making, and we need to know or understand more about the bonding mechanisms involved in any chemical substances. So, in order to understand this theory, what we need to understand is that first we need to know about chemical bonds, which was earlier given by the valence band theory, then followed by the theory of chemical bonding by Linus Pauling, right? Actually, he and his friend G.N. Lewis worked together to develop the complete entire theory about bonding, right? I think in the year 1954, Linus Pauling was awarded with this Nobel Prize for understanding the bonding principles. Okay, let's start with this slide. Isolable concept. You can also say isolable principle, isolable analogy, whatever way. There are many names for that. So any similar word you can use in terms of concept. Okay. So latest picture of Roald Hoffman during year 2000. Okay, these are the key points, right? This is useful. The theory is useful in understanding complex organometallic compounds, their composition, structure, and the concepts and developments of synthetic strategies. So three ways. Okay, complicated structures has been identified, and you can use it for your own synthetic strategies. So both the ways it will help you. Okay, what does it mean? What is the definition for that? The molecular fragments are isolable if the number, symmetry properties, approximate energy, and shape of the frontier orbitals, as well as the number of electrons in them, are similar, not identical, but similar. Okay. We all understand covalent bond in a perfect way, right? So covalent bond has been formed when two groups, mutually share their electrons, to form pair of electrons to develop a covalent bond, right? And for that, the atoms which help in binding the two groups must have similar energies. Again, last one of the two lectures I showed the molecular orbital diagram and explained about why electronegative compounds are, the energy levels of more electronegative compounds lie in the lower level, and the electropositive compounds, the energy levels stay at the top, and why there is a difference. Right? All those things I had explained. So I wanted to make you to understand this concept better, because of which I explained at that time. Okay, if you want to show two groups as isolable, you have to use this symbol. Okay, symbol double-headed arrow with a orbital. Okay, orbital symbol. Right. So simply you can see any octahedral molecule for which you can consider the fragments. Okay, octahedron is Ml6, metal with 6 ligands. Okay, or 6 donors. Right, and you can break metal and ligand bond, and you can create fragments, Ml5, Ml4, Ml3. Right, so we don't break it further to Ml2 and Ml1. Let's leave that. Right, here what we try to say is that these groups are all something similar to that of the tetrahedron CH4. I mean, the fragments generated from tetrahedron. Okay, in CH4, if you break one CH bond equally, right, you can create a CH3 dot. Okay, CH3 dot, and 2 hydrogen atoms. You can make CH2 2 dots. Okay, the 2 dots represent 2 electrons in 2 different orbitals. Okay, think about the triplet carbene. Right, and you break another CH bond, you will get CH with 3 dots. Therefore, all the 3 dots are occupying each orbitals in order to have equal energies. Okay, you can't have such fragments separately in a bottle, but during the course of reactions it may form. However, here you don't think about any reactions. You just theoretically you can take. Okay, don't think that how CH3 dot we can isolate, and in that aspect. Don't think in the aspect of experimental reactions. Whereas just as the theory, you can just note it down here. Right? You break or you cleave this Ml bond equally to M dot and L dot. Like, don't say that it is a free radical. Okay, it's a fragment. Okay, the moment when you see any one single dot electron present in the molecular group, you immediately call it as right. It's a free radical. Right? Don't say that here, because we are not doing any experiment over here. Just theoretically, we are trying to understand by cleaving this Ml6. Okay. Now, in the point of view of our molecular orbital diagram, you will see, right, Ml6 is the linear combination of metal orbitals with the 6 ligand orbitals, isn't it? Right. So you see, now you see metal T2G orbitals are there in the left side. Take the pen to scribble so that you can show the place where exactly I'm touching. Okay, this is the place, metal frontier orbitals of metal. Okay, and here 6 ligands without metal, 6 ligands of equal energy. Okay, don't think that this is lowest and this is highest. Actually, it should be like this. All 6 must be of same energy. 12 electrons we have. Okay, and if metal consists of 6 electrons, then 6 plus 12, totally overall 18 electrons. Okay, this is how a complex has been formed. Whether this is an organometallic metal carbon bond, or otherwise just simply a coordination compound, whatever it is. Okay, this is how it forms 18 valence electrons for a complex. Okay, suppose if it is Ml5, right? You remove one electron, one ligand out of it. Here in this case, what happens is you have same 5 ligands. Instead of 6 ligands, we have only 5 ligands, so totally 10 electrons. And here, the metals will be having, right, 6 plus 1, 17 electrons. The odd electron comes from, when you cleave the bond, the one single electron. So in this case, we can have, I am sorry, I didn't put the examples over here. Right, you can simply write like one of the orbitals is having a single electron. Okay, here also you have one single electron. Right. So this is D7 complex with Ml5 group. Okay, which is isolable with CH3 dot. So you see this one and this one having each one electron in one of these orbitals. So this part is completely filled. And this part is also completely filled. Whereas this is the only one orbital where you have single electron. So if you happen to have this kind of CH3 dot in organic chemistry, what will happen? It tends to dimerize very easily to form, right? It tends to dimerize easily to form ethylene. Okay, similarly, this also, your organometallic compound, that fragment also has the tendency to form a dimer. That is in the last class I have told you, the metal with odd atomic number tend to have dimeric structures. Okay, because it consists of odd electrons. Right? It consists of odd electrons. Therefore, it tends to bind each other to form a dimer similar to that of ethane. Okay, this is how the theory has been acting as a bridge between both organic as well as inorganic complex. Now, especially you can see co-dimerization. That means like you see how we say co-education. Similarly, co-dimerization, like this part, the organic part and inorganic part, both of them joining together to form this kind of molecule. Okay, theoretically you can write and check whether this is possible. Actually, it is possible. This complex is known CH3 Mn CO5 Me. This complex is known. This complex is important for many catalytic applications where carbonyl insertion reactions have been observed. Okay, right? Carbonyl insertion reactions have been observed for this kind of complex. Right? So you can introduce a new group, organic group, into an inorganic complex. It is possible. Okay. So here some examples are given, like cobalt, right? Cyano complex. This doesn't come under, although there is a metal carbon bond, this will not, we will not study this under organometallic chemistry, right? Because we study extensively in coordination chemistry itself. Okay, so you can make examples for these compounds, not only with the organometallic chemistry, but also with simple coordination compounds. Similarly, you see This has been formed. This dimer has been formed. The same cobalt with the 3 minus, right? As it consists of 17 valence electrons, it can bind to form cobalt-cobalt bond and form. This is actually 6 electrons, 6 minus. Okay. How do you extend this theory? Right? We can extend this theory from the organometallics and organic groups to coordination compounds. Okay, and you can include to any other fasting systems or silane systems and any other systems. Right? So you can change. I mean, what I wanted to say is the ligand part you can change to create isolobal fragments. And you can also change metal part. You see, down the group you can move and you can change metals. Okay, manganese, technetium, and rhenium. Okay, the isoelectronics of metal plus partial carbon monoxide and ligand exchange. It is possible. You can change metal from other groups. So basically, depending upon the number of electrons of the metal, you can also form isolobal fragments. So basically, if you have 17 valence electron, you say this ion complex also isolobal, therefore this will also consist of 7 valence electrons. Okay. And you can remove 3 carbon monoxides and you can include 1 CP group. Right? How? Right? Cyclopentadienyl cation. I'll draw here cyclopentadienyl cation. I'm sorry, anion. Cyclopentadienyl anion is consisting of 6 electrons. Right? This is a 6 electron donor compound. Therefore, you can remove 3 carbon monoxides and you can introduce 1 CP group. And this is having negative charge, and this positive charge will get cancelled. You will get a neutral complex. Correct? Okay. Fine. You see, D7 Ml5. You can remove 2 electrons and you can add a ligand to form D5 Ml6 type of compound. Okay, D7 Ml5 will be equivalent to that of D5 Ml6 when you remove 2 electrons and add a ligand to it. So this kind of ligand electron exchange also possible. Okay. So here in this, from this slide, we have learned that in isolobal fragments, either we can change the ligands or change the metal. Okay, here you can change the ligand with ligand as well as metal both. Okay, along with different kinds of coordination modes, and also the charge, if you have 2 minus charge, which can be exchanged with another ligand, okay, with the different metal environment. You can see. Okay, this one FeCO5 is a neutral compound. CrCO6 is also a neutral compound. This is Ml5 type. This is Ml6 type. Both are 18 valence electron. You remove 3 carbon monoxide and add a CP group, you will get this CP, CO3, Cr. Right? Similarly, as we are talking about fragments, now let us consider the isolable fragments of methyl groups, right? So basically, manganese pentacarbonate, which are isolable with many other elements. Then cobalt you have CO4 and vanadium CO6, Cp, CO2, Fe, where iron, you can replace iron. Instead of iron, you can introduce ruthenium or osmium down the group. Similarly, chromium also down the group, you can introduce these elements. Okay. Right. So if you try to understand this point here, this is basically the metal with the ligand, the isolable fragment part. This is the whole complex where if you fragment, right, as this part is isolable with methyl group, so overall this molecule is also isolable with the overall molecule of organic compound. Okay, similarly you can see. So instead of Cl minus, you can also introduce Sr dot, Cl dot. You can introduce Sr dot. Okay, wherever you have single bond, you can break, make it into 2 electrons, separate the 2 fragments, and you can make exchange of these fragments. It is possible. Right? I'm not going much into detail because we have to move to study about the clusters. You see. So you look at the second one. You have phosphine, right? Diphenyl methyl phosphine, right? Methyl group you can remove and you can add any 17 valence electron containing group. Okay, here also on the silyl part, you can introduce any 17 valence electron containing metal organic part. Okay, so once if you understand this concept, right, when you see this kind of structures, right, it won't make you to feel fuzzy that something weird is there. It is very difficult to understand. No, simply you can remove some groups, and based on that similar isolable fragment you can introduce. See how easy it is. So likewise, you can make also molecules like this. You can design your own substance with isolable fragments, and you can generate new things. Right now, you remove 2 ligands. When you remove 2 ligands, you have, don't say that it is empty orbitals. Both orbitals are having 1 electron each. Okay, so here the molecular orbital diagram indicates, you see, a D8 metal can form Ml4 having 16 electrons. Okay, 2 more electrons you can add to make it as 18 valence electron compound. Okay, you see, they say that iron tetracarbonyl is having 16 valence electron. Okay, 16 valence electron count. Therefore, it is similar to that of CH2 group. Maybe I'll explain you one simple thing so that it will be easy for you to understand further. I forgot to mention about that. Okay. Octet and 18 valence electron. See, when do we see about octet configuration? We see octet configuration for all p block elements, particularly carbon content, right? And 18 valence electron for almost all transition metal complex. Okay, if you say CH4 methane, which is completely octet, and here 18 valence electron is complete complex like chromium hexacarbon. This is a compound which is having 18 valence electron. Right? Both of them are isolable to each other. Okay, whereas in the case of CH3, you say one H dot is gone, therefore this is 7 valence electron, which is isolable with 17 valence electrons of configurations similar to that of any metal complex. And if you have 6 electrons in any octet structures, tetrahedral structures, and it is, we can expect that it is equivalent to 16 valence electron compound. 16 valence electron octahedral compound. Okay. Then 5, if you say 5, then 15. You say 4 electrons, just only carbon, right? Just only carbon having 4 electrons in all the S and P orbitals. This is something isolable to 14 valence electron compound. And this has the tendency to form 4 bonds. This can form 3 bonds. This can form 2 bonds, and this can form one single bond. Okay, if you move more amount of electron deficiency, I mean, this is actually, instead of octet, you are removing electrons from this octet configuration and making it as electron deficient, right? If you move towards this side, okay, the compound tend to form, I mean, this fragments tends to form clusters. Okay, the reason why is, so these are all monomeric. The filled orbitals, very happy to be with this kind of system with just monomers. If you have this one electron deficiency, they can join together to form only one single bond. A cluster will not form. Okay, they form dimer. Right? When you move further down this way, this can form compounds like this, and 5-4 if you go, this will tend to form clusters. Okay, actually the electron deficiency, the compounds or in the fragments makes them to join together to form cluster. Once when they form the cluster, they have filled configuration. You got it? If, for example, I'll go back. I told you this is an isolable fragment. I have to go previous. Yeah. This is just an isolable fragment which is having electron deficiency, but once after forming this compound, dimer, now the 2 electrons are here. Like if you want to count for this part, this will have this manganese will get 18 valence electron count. And here these 2 electrons are common for both the manganese. Therefore, if you count for this manganese, this will have 18 valence electron. This fully filled. Okay, so metal bonds are formed in order to satisfy the electron deficiency. Okay, in order to achieve the fully filled configuration. Therefore, if you extrapolate this to the cluster structures, in cluster structure, more number of metal bonds are formed. Okay, any compound you look at the clusters. Most often, in the clusters, we tend to one atom tends to bind with 3 other atoms. Okay, if you take a cobalt cluster, one cobalt will bind with 3 other cobalt atoms. That indicates that the metal fragment is so electron deficient that in order to make it a fully filled configuration, right, it tends to join with more number of other electron deficient fragments so that the cluster will be formed. I hope you understand this point. Yeah, here we are. Right. So if you have the isolable fragment like this, and you see the orbital symmetry is also like this. So similarly, how the carbon compound, right, they form, ethylene. Right. Similarly, here also you will form metal-metal double bond. Okay, now you have two metal-metal bonds. Don't say that this is one single metal-metal bond. Now you have two metal-metal bonds. Similarly, co-dimerization, whether is it possible? Yes, it is possible. You'll be studying about carbenes. Okay, don't get frightened to study about carbene compounds. Simply use this isolable strategy. Okay, you can understand that part very easily. Right. Similarly, this is a double bond which undergoes addition reaction with the carbon monoxide. This is similar to that of this kind of structures. This is known. So similarly, this can also form structure like this. Okay, many complex structures. So complex structures can be understood based on, right, this isolable analogy. So this compound exists, and this is something similar to CH2. CH2. This is actually CMe2. CMe2 is also isolable with CH2. Okay, so CH2 group is isolable with this group, this fragment. Therefore, you can simply substitute this part over here. See, this compound is obtained, methylene diiron complex, right? And FeCO4, we know that FeCO4 is isolable with osmium CO4, because osmium is down the group of ions. So you substitute all the carbon atoms here, right? You substitute all the carbon atoms. You can form this kind of cluster. Okay. Right. Any compound, any molecule you see, right, based on their electron count and their orbital symmetry, you can prepare n number of compounds like this. Okay. The isolable analogy. In spirocyclic compound, similarly, spirocyclic tin compound can also be synthesized. Now let us see how. So D8 compound, FeCO4 we have seen, and if you move to D7, Mn complex, where you have to add an electron in order to make it as D8. Okay. Iron actually in neutral state D8. Manganese is D7. You have same number of ligands, CO4, right? And if you want to change the metal in the first row transition series, the next metal, right, before that, so D7, okay, you add an electron to it. Just simply add one electron to it, you will get M and CO4 minus. And this is also D8 now. So both are D8 and same number of ligands. Therefore, these are isolable. Cr2 or even CH2. In fact, we have studied so far with CH2. Now, as hydrogen itself is isolable with alkyl group, okay, you can write it as Cr2. Okay, same thing. You can introduce Cp group. Okay, instead of negative charge, you can introduce the hydrogen here, because negative charge indicates that there is an electron, extra electron is present. Instead of extra electron, you can bring a hydrogen atom. Okay, next you can extend it to cobalt system, and also cobalt down the group you can introduce rhodium. Okay, this is D8, this is the D9, and for D9 you have to include this both the part and convert to the cobalt complex. Okay, see this actually this compound is known with rhodium double bond, which is isolable to CH2. So far we see only with the carbon monoxide. Now you see heterolytic, both Cp and CO. Okay, whenever you see any structure like this in CSAR, right? Examination, when you don't have any clue what to do with that, you try to break it into the similar isolable part. Right? You count the number of electrons for this part, then easily you will understand what to be done. Okay. Right. Now we can extend C to silicon, germanium, and tin. Right? Anything in the periodic table you can see. Problem in the slide, handwriting. Any doubts so far? Students, if you have any doubt, please let me know.
Sir, please show last slide.
Just a minute. My computer actually hanged. The Microsoft PowerPoint is not working properly. I have closed it. I'll open it again and I'll check. Otherwise, if you have any other question, let me know.
Sir, if you are replacing, like you said an example, we can replace methyl group with a bigger cluster. So won't there be any space issues, sir, like a steric issue like that?
What do you mean? Actually, say I don't say that we can replace methyl group with a cluster, right?
No, sir. Like
the isolable fragment.
Yes, sir. That isolable fragment, if we are substituting, means will there be any space issues?
Very good, very good question. Actually, the compound itself does exist, right? The isolable fragment, what we say, M and CO5 itself, that does actually exist without any steric hindrance. That can exist. Therefore, the same thing, that the one which is existing thing, we are actually replacing it in the place of CH3. So there is no problem, absolutely no problem. And the size of and we don't use any such kind of bulky groups. So far, whatever we have discussed, we don't discuss about any bulky groups. All groups are very simple things like carbon monoxide, methyl group, right? If you think about tertiary butyl tris tertiary butyl silyl group, Okay, if you say that, just a minute, I have. I hope you can see my screen. See, if you think about, pick up the pen. See, hydrogen is isolable with CH3. Dot. And also this is isolable with Si dot tertiary butyl. This group is so bulky. Okay, if you try to bring a bulky group in that place in CH3 itself, right? If you try to bring one silicon group with T-butyl 3, if you try to bring these groups very close to each other, then you will feel that this is sterically hindering. Right? Then totally different kind of mechanism you have to look at. Okay. So whenever this kind of sterically hindering or very bulky groups are introduced, most often the electron deficient compound itself will get stabilized. Okay, for example, I'll tell you, right? Titanium ET4. This is isolable with the TiCl4. You agree with me or not?
Yes, sir. Yes, sir.
This exists. We can prepare this compound, but we cannot prepare this compound. This is totally unstable. Okay, so what the instability is because of beta hydride elimination. Therefore, you can try to synthesize isolable compound Si, Me, not Me. Ti, CH2, Si, Me3. This group is actually called silapentyl group. Okay, you can prepare this compound. In fact, as this group is sterically hindering group, I mean, instead of Me3, if you try to bring tertiary butyl group, 3 tertiary butyl group, this becomes so big that you cannot fit 4 ligands of the same kind like this. So you, instead of preparing this compound, you will be only able to prepare this CH2, Si, T-butyl thrice. Up to 3 ligand only you can prepare. Okay, so sterically you can, if you add sterically hindering very bulky group to a metal which is electron deficient, because of the bulkiness itself, the complex will get stabilized. Okay, this is actually entirely a different part. Okay, now we are not discussing about any such kind of very bulky substances. Right? All are very simple things. Even boranes and such kind of things, they are not bulky at all. Okay, even carborane, you say icosahedral structure. Any of the part you fragment and see, they are not bulky groups. Okay, just they are pH units, right? Okay, any other doubts? Okay. So this is a complex compound. We see both platinum and manganese both are there. Platinum manganese bonds are formed. In addition to that, phosphorus is also involved in this cluster. Carbon monoxide is just introduced only to maintain the 18 valence electron configuration of platinum. Okay, if you break these parts, remove these things, then this is just PTCO, and this is something similar to that of ethylene, right? So you take this simple compound and try to bring this kind of thing, okay? Take this kind of group, and you can actually prepare this complex. Similarly, this you break like this, and this is actually equivalent to ethylene, and this is also equivalent to ethylene. Therefore, there will be a phosphorus and then ethylene. You can prepare, but this ethylene part, right? You have introduced a phosphorus here attached to ethylene. Therefore, instead of phosphorus, you have CH2 group, ethylene and CH2, and it binds to platinum. Right? You see Rp2, sorry, PR2 is isolable to CH3. How? This is 7 valence electron compound. This consists of 5 electrons, and instead of methyl group, you introduce 2 hydrogens. Therefore, PH2. Okay, PH2. This consists of 5 electrons and plus 2 electrons. So totally 7 electrons. Therefore, PR2 is isolable to CH3 and isolable to CH2 minus group. Therefore, one additional electron is present. This is also 7 electrons. So based on that, you can form this kind of compound. So any complicated structures you see, you can break it into small things, and similarly, you can add these things. Simple. You see, this is known. Similarly, you can prepare this complex also. You understand? See, most often this kind of structures you can see in the inorganic chemistry part of this CSIR. Right? This is so important that if you know this analogy, you can introduce similar groups and you can understand it very, very easy. Right? Don't think too much about these kind of structures. Simply break and introduce, isolable fragment and understand it. Suppose ML3 type, you remove 3 ligands, you have 3 dots, right? Here one electron, here one electron. So this is something similar to that of CH group, right? So you have, 3 odd electrons. Okay, basically D9 metals. You can choose and you can easily explain these things. And 15 electrons. So overall, it will be 15 electrons. That means 3 electrons less to that of octet configuration of 18 valence electron compounds. Right? See D9, ML3. So cobalt tricarbonyl. So this is the group fragment we consider, which is isolable to CH group. I think easy to understand this part, right? So this actually combined with another of similar type to form ethylene. Therefore, is it possible to make metal-metal triple bond? Yes, it is possible. Metal-metal triple bond. Okay, so if whenever you see any metal single bond, double bond, or triple bond, you don't need to worry about it. Okay, think about this isolable principle. Similar to that of acetylene, it has formed. Right? So co-dimerization, similar, the dimerization, co-dimerization that we have seen earlier, right? So similarly, you can also prepare this kind of structures. Right? You see, this is a cluster. Now we move to the cluster. More, if you make it more electron deficient, it tends to form the cluster structure. Now you see, cobalt, tetracobalt cluster, perfect tetrahedron, isn't it? Yeah, here you see, instead of one cobalt unit, they have introduced a carbon here. In Hughie book or Atkins book, in many places you can see this kind of structure, where in the metal cluster itself, they introduce sometimes hydrogen, sometimes a carbon, sometimes silicon, or even phosphorus. Right? You don't need to worry about it. Okay, you just simply calculate. I tell you here, cobalt is D9. Okay, D9 plus 6 electrons from the ligands. D9, and this is 6 electron overall, totally 15 electrons, right? So immediately you can calculate this part is having 15 electrons. Therefore, 3 electrons less than that of 18 valence electron complex. So isolable analogy states that 15 electron unit of inorganic substance will be equal to the 5 electron unit of tetrahedral structure from carbon. Carbon has 4 electrons. So for 5 electrons, we need to just have CH unit. So introduce CH or CR, whatever you can introduce here. Instead of R, you can also put H or methyl group or any other group in the place of R. Even Cl, you can also place one halogen here instead of R. You'll be able to prepare such structures. And this one also you can remove and you can bring Cr, alkene complex, methylidene complex, and followed by alkene complex. Overall, this is the tetrahedral substance. Similar to organic, total organic substance. So this way you can bridge both organic and inorganic cluster compounds. Now you vary the metal. If you vary the metal, what happens? So based on the number of electrons, right? Number of electrons on the metal, you can bring any charge or other ligands also. See, this is a hydrido compound. You can also write it like Fe CO3 anionic. Make it as anionic. This one and this ion compound both are isolable to each other. Okay, suppose if you choose nickel, right? Nickel consists of 2 electrons already more, D10 configuration. Therefore, you have to remove 1 electron. Therefore, you have to introduce 1 plus charge. Right? Similarly, you can write the n number of compounds. You see, tungsten triple bond, and you can cut this part and introduce the organic group. Okay, similarly, you can take silicon, germanium, nitrogen, phosphorus, arsenic, anything you can introduce, right? And you can prepare a compound like this. So earlier we have seen CH unit, right? CH is isolable with, CR. In the previous slide, you have seen CR, which is isolable with phosphorus. So you can bring phosphorus. Right. So overall, like the summary, you can see. Right, any organometallic structures or any compound, organic compound itself, you see, you break them down into corresponding isolable fragment, and you can reunite or otherwise scramble these things and mix and match to form many structures. Okay, even in this compound itself, there are 3 orbitals, right? In tungsten. This tungsten, you have 1, 2, 3. This place you put CH3, you attach CH3 group, and in this place you can attach this part over here. It is also possible. So this is how you can design your own synthesis strategy. Right? For all synthesis applications, you can use this isolable concept. Right? So many things in chemistry, when we look at the textbook, right, some of the things, if we don't understand what we do, we simply skip that part, right? If you try to understand that part, it will be easy for you to analyze many things. One thing, for example, is that the molecular orbital diagram. Right, when you look at this molecular orbital diagram, I told you this is actually from the principles of quantum mechanics, linear combination of atomic orbitals to form a molecule. Okay, molecule itself, you take only the frontier orbitals. Frontier orbital consists of only HOMO and LUMO. Okay, HOMO and LUMO. If you consider this molecular orbital for a group, right? I don't say it is a molecule, for a group. Okay, this is the group which is going to involve or participate a part of group in a complete structure. Whole molecule or part than our group. Group or molecular orbital structure right? You can attach this group to any other fragments. Right? Only the frontier orbitals, HOMO, will only participate. The entire molecular orbital diagram understand our thing. HOMO and LUMO frontier orbital part. நம்ம ஈஸியா ஒரு கிளஸ்டர் மாலிகுலுக்கு நம்ம ஒரு குரூப் எடுத்து நம்ம ஃபிட் பண்ணிடலாம். எப்படி? both of them must have identical symmetries and also their orbital energies. Orbital energy ரொம்ப அதிகமா டிஃபரெண்டா இருந்தாலும் the compound which you form will be unstable. Okay, stability கிடைக்கணும் என்ன பண்ணணும்? You have to form a strong covalent bond. Strong covalent bond க்கு என்ன வேணும்? The electronegativity difference அதிகமா இருக்கக்கூடாது. That means the energy difference must not be maximum. You should try to bring it as minimum. Okay. I just to show you a few things. I don't need to explain all these things. Now you know the understanding. You understood the basic concept. You can analyze these things very easily. Platinum is also from nickel group. Rhodium is actually from cobalt group. 1 electron less, Therefore, you have to add one electron. Actually, the electron here actually looks like some kind of symbol, but actually this is actually a minus charge on electron. Card, do you know what is card? Card is cyclooctadiene. You have seen this kind of cyclooctadiene, 1,5-cyclooctadiene. So you can just simply break this. You can introduce here. Okay. And this is isolable to nickel. You see, nickel with 2 ligands is isolable to iron. Okay, the total electron count must be same. So if you say this is 16 electron, and this should also be 16. Right here you see, now we have made clusters. You can make large clusters. In fact, even diboranes, boranes also come under this category. There is isolable analogy with these things. Right? This is what we have seen in the last 2 classes. Boranes and carbonyl clusters. Both are having some intercorrelations. The one which links is isolable analogy. Students, any doubt? Any questions? It looks something complicated, right? Let's break it apart. So easily you can see this part, and this part are all same. This is phosphorus group, right? So instead of this arsenic, you can put phosphorus. PME2. If it is something with carbon group, it is easy for us to understand. P, instead of P, you can write it as PH. Okay. And here actually what happens is that there's a problem. Just a minute. Just a second, I'll share the screen. this is a molecule. You have to break it into parts. And I'll tell you, this is easy for you to understand the structure. These 3 units are similar. And these 2 are similar. This is something. No, just a second. Only these things are all similar. These parts are all different. Right? All these 4 are different. Now we'll see one by one. We will see. So let us take this part and count the number of electrons. Chromium has 6 electrons, right? 6 plus. Let's go with any one of the routes, oxidation state method or neutral state method. Right? If you take neutral state method, neutral configuration method, then you have to directly take the number of electron count for chromium, and CP will be having only 5 electrons, isn't it? And sorry, 6 electrons. For chromium, we have 6 electrons. CP 6 electrons, and carbonate you have 6 electrons. So totally, no. Trying to erase this. Don't see the eraser here. Eraser is not working. This is actually 5 electrons, CP. So totally it is 17 valence electrons. Therefore, this is isolable with D5Ml6. Okay, D5Ml6, and which is equivalent to CH3. Right. Next, A is emitter part. Next is linked to A is emitter part. It's actually CH3. I told you this is AS, which is similar to phosphorus, and Mu2 you can make it as H2. Okay, for one phosphorus, you say it is CH equivalent to CH, and H2 means CH3. Right? You got CH3. This is equivalent to CH2 minus. Okay, you have 2 bonds. As we have got 2 bonds, you have to make it as CH2 unit. Okay, therefore this is CH2 minus. And CpCrCO2. You have 5 electrons, 6 electrons plus 4 electrons. So 10, 15. D5 Ml 5 type. Okay, this has 3. This is equivalent to 3 ligands, and you have two ligands, total 5. It's the Cr is the D5 here. Okay, D5 Ml5 type, which is equivalent to CH2 plus type. Okay, CH2 plus. Next, CO CH3. Next, we are moved to CO CH3. Simply Ml3 type, and CO is D9. Cobalt is D9 metal. Therefore, this is again CH2 plus, and these 2 are isolable. D5 Ml5 and D9 Ml3 are now isolable here. Okay, and FeCO4, D8. Fe is D8 and Ml4. L4 ligands are there, therefore FeCO4 is Ml4 type, D8 Ml4 type, which is equal to CH3 plus. So now you change all these groups to these alkyls. Okay, alkyl groups. What will you get? CH3, CH2 minus, CH2 plus, CH2, CH2, and so on. Okay, in this now you cancel all these charges. Okay, minus plus, all these charges can be cancelled entire whole structure as CH3, CH2, 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 CH2. What is 1, 2, 3, 4, 5, 4, 5, 6, 7, heptane, N heptane. Overall, this molecule is having structure similar to that of a heptane. It's a very interesting concept, right? Isn't it? The only thing is that if you just simply understand this, you can design any new chemicals. See, this part, left side part is similar to CH3, right side part is similar to CH2. Now you count and find out what is the isolable fragment equivalent to this nickel part. You can do it. This part is very easy, right? Germanium is carbon group, and this one easily you can replace with H. NSiMe2, Me3 thrice. So this is actually NH part, NH2 part, CNH2. CNH2. Okay, N is CH, therefore this is CH3, CH3. CH3, CH3 part is attached to nickel. Right? CH2, again it should be connected to another CH2. Therefore, this part, this group is isolable with CH2. Okay. Right. Simply CH2. This part. This is CH, right? Only this RuCO3 must be equivalent to CH. Therefore, 3 bonds are there. However, you can't break this bond. The bond break பண்ணக்கூடாது. ஏன்? PPH2 is actually coordinate covalent bond. This is actually a ligand. Okay, this is metal L4 type. Okay, and this is actually CH2. This is also again CH2. Similar to that of. Okay, you can see the literature. Right. Actually, the first one is the isolable concept, bridging organic and inorganic groups. Okay. Very interesting things we can find based on this isolable analysis. I'll show you some cluster structures based on these. Okay. I hope you can see my screen. If not, please let me know. Okay. Suppose if you have this kind of cluster, right? You have to find out what is the structure of this cluster. What will you do? Right. First point. This is the odd thing inside, right? You have a metal complex, metal carbonyl, where you have a CH group, right? CH is isolable with is isolable with a metal, right? With 3 electrons, right? And L3. Correct. So now we should know what is M and what is L3 in this aspect. Here, a ligand is carbon monoxide, therefore it is easy for us to choose carbon monoxide. L3 is carbon monoxide, 3 carbon monoxide. And what metal here we can fit? Okay, basically it should be ML6. Basically here, if you say metal to have all the 6 ligands together, it should have 6 electrons, right? 6 electrons combined with 6 ligands. Therefore, from 12 electrons from all the ligands, metal should have 6 electrons. Whereas in this case, 6 plus 3 and CH equivalent ML3 type should be D9. Metal with D9. That's what we have seen in the slides. Right? D9 metal is cobalt. Okay, therefore CH is isolable with CO and CO3. So CH is isolable with cobalt tricarbonyl. Now we can write this structure as CO4 and CO12. CO4, CO12. Now you know when you have 4 cobalt and so the cluster will be like a tetrahedron. Okay. So all edges of this tetrahedron will be shared by 4 cobalt atoms. Whereas in this case, this is the primary molecule you would like to solve, right? And CO, 3 cobalt, and all these carbonyls, 9 carbons will be shared between all these 3 cobalt atoms. And here is the CH. This will be the structure of molecule. Okay, the cluster structure can be easily understood. So likewise, heteroatoms like phosphorus, instead of CH, you can also introduce phosphorus. Okay, P4, phosphorus P4 molecule also can have the structure like this. Any doubts? Please ask me. Okay. If no doubts are there, I think you have understood this isolable concept and you know how to interchange the organic groups in the place of any inorganic fragments. Right. Only one thing I would like to talk about, then we will end this class. Zintal clusters or zintal ions. Okay, zintal ions, for example, I tell you, tin. So 9 tin atoms can join together to form a zintal ion. Okay, something of this structure it forms. I'll try to draw the entire structure. This is very difficult through this software. However, I'll try my level best to show you how it looks like. Okay, something like this, and 4 tin atoms. 4 tin atoms are at the base. They are planar, and next 4 more tin atoms are there. They are also planar, but the planes are like this way. If you see from the top, it will look like this. If you see from the top, it will look like this. One of the atom, the tin atom, will be on top. Okay, like this. I just put a dot for that. And rest of the other 8 tin atoms are there, present below this tin atom. Now I am encircling it below this tin atom. First level of 4 tin atoms, and then next another 4 tin atoms, which are like not in eclipsed manner. Okay, like staggered structure you can see. This is how it forms. And overall, this tin compound has 2 electron excess. That means it may be like, if you want to form a neutral compound, maybe like NH4 twice tin. Originally, this could be the compound, but this actually forms a cluster. Tin 9 forms a cluster. Right? How to identify this in terms of closo-nido-arachno? Okay, then there is a possibility like electron count you can use similar to that of the boranes. You should know tin comes down the group of carbon. Tin comes down the group of carbon. Therefore, this is similar to C92 minus 8. That way you can write. Okay, isolable principle, you know. Right? Instead of tin, you write it as a carbon, C92 minus. And carbon, how to change? You know, the closo-nido-arachno structures only for boranes, right? And based on this isolabile analogy, now you know how to convert carbon to boron. Carbon is having 4 electrons and boron is having 3 electrons. So in order to make boron as 4 electrons, you have to make this carbon as BH unit. BH unit 9. 2 minus. Therefore, what you will get? You will get n plus 1 pair, right? This is n. N is equal to 9. N plus 1 pair. Will suggest you to close the structure. I'm sorry. Big mistake I have made. That's why I'm just wondering. This is actually 4 minus. So overall 4 minus, 4 electron excess. So C9 4 minus. So N plus 2 pairs. And this is nido structure. Okay. Nido is correct. And I made a simple mistake that it should have 4 minus. So SN4, SN9, 4 minus. This is simple and general. Okay, similar kind of structure has been observed for this is actually G, germanium 9 2 minus. I am sure about it. Germanium 9 2 minus, which is actually a closed structure. Okay, in this case, I would like to ask you to solve for BI4. Two minus. Can you try? Bismuth comes down the group of nitrogen, right?
Fifth group, sir.
Therefore, this is equivalent to pH, which is equivalent to BH2. Written. So this can be simply written as BH2 4 times 2 minus. Actually, we know one BH unit consists of 4 electrons. We are simply solving this 4n rule, right? We are following 4n rule. Therefore, you write Bn, the BH unit should be separated 4. Totally, you have 8, right? Plus 8 hydrogen atoms. Therefore, H plus 2 electrons. Right? So So this is n plus 4 plus 2, 6 electrons. Therefore, n plus 3 pairs, skeletal electron pairs is n plus 3. Therefore, equal to, which is equivalent to arachno.
Arachno, sir.
Very good, arachno. This way you can solve very easily for Zintel clusters also. Sometimes they complicate this cluster by incorporating heteroatoms. Okay, bismuth itself, they can introduce heteroatoms. In that case, again, you convert back to carbon and then bring it again to BH units, make it into BH units, and then count number of electrons, and then you'll be able to find out which type of cluster, whether it is closed zone, nido, or arachno, very, very easily. Yeah, doubt irukappa? சரி, லாஸ்ட் 2 கிளாஸ்ல வந்து நான் இது மாதிரி நிறைய டிஸ்கஸ் பண்ணோம். ரைட், கிளஸ்டர்ஸ், பர்டிகுலர்லி metal carbonate clusters and boron carbonate type of clusters. Anybody found any interesting question in CSAR and you would like to discuss over here too in front of all these students? ஏதாவது ஒரு ப்ராப்ளம் எடுத்து நீங்களாவே ஏதாவது சால்வ் பண்ணி காமிக்க முடியுமா? யாராவது ரெடியா இருக்கீங்களா? இது ஒன்றும் இல்லப்பா, பேசிக்கலி எலக்ட்ரான் கவுண்ட் தான். எலக்ட்ரான் கவுண்ட் நமக்கு பீரியாடிக் டேபிள் ஆஃப் எலிமெண்ட் தெரிஞ்சாவே, பீரியாடிக் டேபிள் நல்லா ஞாபகம் இருந்தாவே நம்ம ஈஸியா எலக்ட்ரான் கவுண்ட் கண்டுபிடிச்சோம். ஸோ எலக்ட்ரான் கவுண்ட்டையும் ஐசோலோபல் ஃபிராக்மெண்ட்டையும் சேர்த்துட்டீங்கன்னா ரைட், எங்கெல்லாம் கஷ்டமா இருக்கோ எல்லாத்தையும் சிம்பிளிஃபை பண்ணி, எவ்வளவு காம்ப்ளிகேட்டடா ஸ்ட்ரக்சர் கொடுத்தாலும் அதை பிரேக் டவுன் பண்ணி ஈஸியா அண்டர்ஸ்டாண்ட் பண்ணலாம். ஓகே, ஒரே ஒரு இம்பார்ட்டன்டான ரொம்ப 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 இம்பார்ட்டன்டான பாயிண்ட் நான் சொல்லிட்டு நான் முடிச்சுக்கிறேன். இது வரைக்கும் அதை பத்தி நம்ம பேசல, ஆனா ரொம்ப ரொம்ப முக்கியம், அதை சொல்லிட்டு நான் முடிச்சுக்கிறேன். இந்த ஹைட்ரஜன் அப்படின்னு ஒன்று எடுக்கிறோம் இல்லையா, H டாட் அப்படின்னு எடுக்கிறோம். வாட் டஸ் இட் மீன்? இட் இஸ் ஆக்சுவலி an atom which consists of one nucleus and one electron around it, right? One electron. So one electron system. If you write it as H, if you write it as H minus, it's going to be atom having 2 electrons. Seriya, you can actually bind with CH and H minus to make CH2 minus unit. நம்ம ஒரு எக்ஸாம்பிள்ல பார்த்தோம் இல்லையா, CH2 minus CH2 plus அப்படிலாம் பார்த்தோம். So CH2 minus, CH2 minus unit is basically CH3. ஏன் அப்படின்னா, இந்த ஒரு ஹைட்ரஜன் இருக்கு இல்லையா, ஹைட்ரஜன் ஆக்சுவலி இஸ் ஐசோலோபல் டு 1 எலக்ட்ரான். இந்த பாயிண்ட் நம்ம இது வரைக்கும் நம்ம பார்க்கவே இல்லை. இது நான் அப்பவே சொல்லியிருக்கேன், நான் மறந்துட்டேன். பட் திஸ் இஸ் இம்பார்ட்டன்ட் பாயிண்ட். H டாட் இஸ் ஈக்குவல் டு 1 எலக்ட்ரான். இது எதுக்காக சொல்றேன் அப்படின்னா, இங்க எங்கெல்லாம் இந்த சார்ஜ் வருதோ, இந்த சார்ஜ் வர்றதுல நீங்க என்ன பண்ணலாம், 2 எலக்ட்ரான் போற இடத்துல 2 ஹைட்ரஜன் ஆட் பண்ணிக்கலாம். H டாட், 2 electrons are equivalent to 2 hydrogen atoms. போட்டீங்கன்னா ரொம்ப சிம்பிளா இருக்கும். சரியா? ரைட், CH3. அப்ப CH3 வந்து நம்ம சார்ஜ்டா எழுதணும் அப்படின்னா CH2 மைனஸ் அப்படின்னு எழுதிக்கலாம், ஒன்றும் தப்பு இல்லை. இங்க வந்து இந்த ஆர்கானிக் கெமிஸ்ட்ரி பிரின்சிபல்ஸ் எல்லாம் பாக்குறீங்க. இது கார்போ கேட்டையான், இது கார்பேனியான், இது வந்து நியூக்ளியோஃபைல், அந்த மாதிரியான கான்செப்ட் இங்க பார்க்கவே பார்க்காங்க. நம்ம வந்து ரியாக்ஷன் பேஸ்டா நம்ம இப்போ பார்க்கல, ஸ்ட்ரக்சர் ரிலேட்டடா ஸ்ட்ரக்சர்ல இருக்க தியரியை மட்டும்தான் நம்ம பார்த்தோம். ஓகேயா? அதே மாதிரி இந்த குரூப் இருக்கு அப்படின்னா CH2, இதுல வந்து ஒரு புரோட்டான் ஆட் பண்றோம், H+. ஆட் பண்ண அப்படின்னா என்ன கிடைக்கும்? CH3 plus. எலக்ட்ரான் கவுண்ட் எத்தனை? What is electron count for CH3? Valence electron count.
Seven, sir.
CH3 க்கு 7 பா. CH3 plus க்கு CH3 7. அதுல பிளஸ் சார்ஜ் கொண்டு வந்தா ஒரு எலக்ட்ரான் எடுத்துன்னு அர்த்தம்.
6 sir.
அப்ப 6 electrons.
6 sir.
6 electrons is equivalent to CH2. கரெக்ட்டா? அப்போ CH2 ன்னு எழுதினாலும் ஒண்ணுதான், CH3 plus அப்படின்னு எழுதினாலும் ஒண்ணுதான். H plus ஆட் பண்றதுனால எத்தனை H plus ஆட் பண்ணாலும் அதுல வந்து no change in valence electron count. No change in valence electron count. இந்த பாயிண்ட் முக்கியமான பாயிண்ட் பா தெரிஞ்சுக்கணும். நீங்க எத்தனை H plus வேணாலும் ஆட் பண்ணிக்கலாம். ஏன்? நான் சொன்னேன் இல்லையா, ஹைட்ரஜன் ஆட்டம் அப்படின்றது it is actually one proton and one electron. If you make it as H plus, this electron is removed, you have got only one proton. எலக்ட்ரானே இல்ல. அப்ப எத்தனை H plus ஆட் பண்ணாலும் அங்க எலக்ட்ரான் கவுண்ட்ல சேஞ்சே இருக்காது. சோ ஐசோலோபல் அனாலஜில இது ஒன்னு தெரிஞ்சுக்கணும். சரியா? அப்போ CH3 ஐசோலோபல் பிராக்மெண்ட்டுக்கு CH2 மைனஸ் னு எழுதலாம். சரியா? ஒரு ஹைட்ரஜனை குறைச்சு எழுதிக்கலாம். CH2 வந்து ஐசோலோபல் பிராக்மெண்ட்டுக்கு இந்த ஆர்பிட்டால் சிம்பிள் போடல பாருங்க. போட்டா அவ்வளவு தெளிவா வர்றதில்ல, அதனால நான் டபுள் ஹெடட் ஏரோ மட்டும் யூஸ் பண்றேன். பட் when you write it as ஐசோலோபல் சிம்பிளோட எழுதுங்க. CH2 can be written as CH3 plus. சரியா? ஓகே, பாருங்க இந்த CH2 மைனஸ்ல ஒரு H plus ஆட் பண்ணுங்க. You get this. இதுல ஒரு H plus ரிமூவ் பண்ணுங்க, you will get this. So H plus ஆட் பண்றதுனால, புரோட்டான் ஆட் பண்றதுனால there is no change in the valence electron count. At the same time, minus charge இருந்தால், when there is a negative charge that indicates extra electron, it can be counted similar to one hydrogen atom, H dot. புரிஞ்சிருக்கும் நினைக்கிறேன். சரியா? So in nutshell, I just summarize this class. This class we have understood about isolable concept. Very beautiful concept and important thing to analyze the structure of any organic as well as inorganic compound, and you can make a bridge between them. You can prepare a compound which is combining both organic as well as inorganic groups. And when you look at the clusters, more the when a fragment is having more electron deficiency, then it tends to form more complicated clusters because it is having want of electrons, because of which it tends to form a more complicated structure. And the complicated structure can be easily understood by breaking them into small pieces as isolobal fragments. சரியா? Right? And finally, I told you how it is analyzed with Zintel clusters. சரியா? இந்த Zintel ions இதெல்லாம் பார்த்தலாம் பயந்துக்காது. ஒண்ணுமே கிடையாது. சிம்பிளா வந்து போரானாவோ இல்ல கார்பனாவோ கன்வெர்ட் பண்ணிட்டோம், ஐசோலோபல் பிராக்மெண்ட்ஸ் கன்வெர்ட் பண்ணிட்டோம், ரொம்ப ஈஸி. ஃபைன். இதுக்கு முன்னால 2 கிளாஸஸ் பார்த்தோம் இல்லையா? அதுல ஃபர்ஸ்ட் கிளாஸ்ல வந்து we have looked at the structure of how to find out the structure of cluster boranes and carboranes. The carboranes again, boranes to carborane conversion again we have to use this isolable principle. So yeah, those things I have already explained. In the second class, I have mentioned about the understanding the structure of metal carbonates, how to identify number of metal-metal bonds, how to do the electron count, right, and also how to understand the structure of polynuclear metal carbonates. அதில் கார்பனைலோட டிஃப்ரெண்ட் கைண்ட்ஸ் ஆஃப் கோஆர்டினேஷன் மோட்ஸ் இது எல்லாமே டிஸ்கஸ் பண்ணோம். பாண்டிங் பார்த்தோம், எப்படி எந்த பாண்டு ஸ்ட்ரென்தன் ஆகுது, எந்த பாண்டு வீக்கன் ஆகுது, அதை எப்படி ஐஆர் ஸ்பெக்ட்ரோஸ்கோப்பில் அண்டர்ஸ்டாண்ட் பண்ணுறோம், அதை வச்சு ஐடென்டிஃபை பண்ணுறோம். எப்படி எந்த டைப் ஆஃப் மெட்டல்ஸ்க்குலாம் யூ ஹாவ் 3 center 2 electron bonds, I mean bridged carbonyl bonds, and இதெல்லாம் only terminal bonds form. In the நிறைய concepts we have discussed. Okay, and finally today we have discussed about most important concept. The concept மறக்கவே மறக்காது. So at least do practice with this one at least once in a week time. Okay, and the anguivantic chemistry paper part. That was the actual literature, actual lecture provided by the person who understood this isolable concept first and derived it, Professor Hoffman. Okay, so don't get frightened about looking at the molecular orbital diagrams. Don't get frightened on looking at any complicated structures. All these things are all, after all, very simple things if you break it down to carbon and hydrogen and try to correlate it with simple organic structures. Okay, if you have any doubts, please let me know, or otherwise we will stop the class.